we will be seeing how to serialize and deserialize a binary search tree. What does a binary search tree mean? A binary search tree means that whenever you have a root node, on the left subtree, the node that is going to exist is going to have a value that is lower than the value at the root, and in the right subtree that you have, the value is going to be higher than the root node that you have. This is what we mean by a binary search tree. And the problem statement says that we have to encode this input of a binary search tree into a string, and then we will be deserializing, that is decoding this string back into the tree itself. And these are the two parts that are going to be involved here. First step, you serialize into a encoded string. The format of this string is free. We can choose whatever way we want to encode, and then this string will need to be decoded back into the binary search tree in the same original tree structure that was provided as a input. So that is the whole aim here. And to reach a solution, what we will do is traverse this binary search tree in a post-order traversal. And what does post-order traversal mean? Post-order traversal means that first we will be visiting the left node, then we visit the right node, and then we visit the node itself. So first we have the root node that we have received. We traverse the left subtree because of this post-order traversal. On the left you have a 1. First 1 will come, then we will go to the right subtree. We have 3 here, and then we will come back to the root that was provided. So this is the post-order traversal order. Now what we are trying to do here is, whenever we want to serialize, that is encode, we will encode in this pre-order traversal format, and we are going to decode, we will backtrack with this pre-order traversal format being the center of it. Because we know how we have encoded, we also will know how do we have to decode. So whatever sequence we went in for pre-order traversal, then we have to just come back in a reverse manner considering this pre-order traversal, and making sure that we follow this rules of BST, wherein the left subtree will have values lower than the root node and the right subtree will have values higher than the root node. And to do that, we first build this pre-order traversal sequence that we have. So we went from left, then right, then the root itself. This sequence I will encode it as a string. So this becomes a string with a value that is separating them. Let's put spaces between them to separate. So I will say 1 space 3 space 2. So this is my encoded string that is going to be available with us. Now this encoded string I will trace back in this pre-order traversal sequence going in reverse and construct the original root binary search tree that I was provided. And how do I do that is something like this. I will convert this back into an array. So I received this as a array in this sequence, encoded this input that I have received into a string. Now this specific string I have to decode now, and to decode it, how can we go about? So for decoding, I will say convert this back into array. So I will have 1 3 2 again, which is going to be my array. Now from this array I will build back my binary search tree, and to do that I will first go towards the last element that I have in my array, which is going to be 2. I will pick this 2. I will say the right side of this 2 is going to be the immediate next element associated with it. Why the immediate next element? Because when we went in the sequence was left, right and root. So now you have root here. After the root, the immediate next element is going to be your right, and in that sequence I will say the right element is going to be the immediate next, and the one after that is going to be my left. and the one after that was 1. So I will keep popping this array that I have and reconstruct my original binary search tree that I had received. Now when I reconstruct it, I cannot just keep on going and popping and saying put 1 to the right when put 1 to the left. We have to follow the binary search tree rule, which is going to be that on the left side, whatever value you are going to have has to be lesser than the root node, and on the right side the value has to be higher than the root node. So we have to always maintain that 1 has to be less than 2 and 2 has to be less than 3. This is the order that will be maintained, and that's pretty much it in terms of the logic. We encode using Postorder Traversal, and then we decode by reverse tracking with this Postorder Traversal, and this reverse tracking will also happen in a recursive manner. When we do this Postorder Traversal, we will go in a recursive approach, and when we do deconstruction of this tree again, we will also go in a recursive fashion. And how that will look in terms of code is something like this. So we will have a serialize function. We will also have a deserialize function. The aim here with this serialize function is going to be you take the root that is going to be the binary search tree that you have received. To do a Postorder Traversal, I can just say something like this. So Postorder Traversal, I will take a root here and I will say return it in a Postorder Traversal fashion. So first I have to return left, which is going to be my root dot left. Then I have to return the right element, which is going to be the right subtree, and then I return the root itself, which is going to be root dot value. Now I know that when I reach the leaf nodes, there are not going to be any left and right children, so I need to put a edge case here, and the edge case is going to be if root that I have is going to be null. In that case, I will just return empty. And then the next step is I don't want 2D arrays, I just want a flat array. So to do that, I will just put destructuring here so that I will have a flat array rather than a 2D array. So this will give me a Postorder Traversal order in the form of an array. I will go in my serialize function. I will say that the list, which is going to be the traversal list that I'm going to have, is going to follow this Postorder Traversal. Now, once I have this list built with me, the next step is to pass it as a string, because right now I have written from here as an array. And I will just say whatever input I have, put a space after that and construct a array out of it. And to do that, I will just say join with a space and return this as my encoded string. And let's say you have the order which is 1, 3 and 2. It will put a space 1, 3 and 2 and return it as part of my serialize function. Then the next step here is that I want to now deserialize and bring my back now. To bring it back, I will take this as an input, because deserialize is going to take the serialized value, which is going to be the encoded string, as an input. So this data is the encoded string itself. So from the encoded string, I will say that the traversal list that I want to bring is going to be data that I have received dot split. So because I have received an encoded string, I want to convert it now back into an array. And to convert it back into array, I can just say dot split. And when I split, I will split by the spaces that exists in the array. And because this split is going to give me string values, what I am looking for is integer values and not string values. And because of that, which I then map with the character value being there, and that value is going to be passed int of that value itself. So this is going to give me an array of integers. Then basically I have this array which I encoded into a string. From that string, I built back my array again using this split function. Now this is the original array of the traversal order, which was post order. Now with this post order traversal in mind, now I have to deconstruct. And before deconstructing, I will just put a edge case wherein if traversal list is empty, then I will just return null, so that I handle the edge cases that exist. So this will mean that the root itself is null. And to reconstruct, I will say something like construct my BST again, and to construct it, I will pick this traversal list of pre-order traversal that I have with me and go in a reverse fashion rebuilding. And to do that, what I will say is whatever traversal list I have received, so I will pick the value from it, and the value is going to be from this traversal list the last value that I have. Same thing we did here. We had 1, 3 and 2. I picked 2 from here, and that value is going to be traversal list.length minus 1. Whatever value I have, I will construct a root node from that value itself, the last value in the first iteration, and that will look something like this. So I will just say root is equal to new tree node, and I will just pass whatever value is supposed to be used. And the aim here is to return this binary search tree that we are constructing, and in the end you just return the binary search tree that has been constructed with the root node. Then we said we want to now go in a reverse fashion. What do you mean by reverse fashion? We went from left, right, and then we went to the root. Now we picked the root here. So the next step is picking the right value. And to do that, I will just say root.right is going to be again a recursive call. And that recursive call will just say construct the binary search tree for the right subtree again with the new list that you have, which is now going to have the next value as the last element. And to have the last value as the element, I need to pop this list that I have. So whatever list I have with me, I will say just pop the list and then move forward. Similarly for the left node, so after you pop and you go towards the right node, then the next step is to go towards the left node that you have with you. And to do that, what we will simply say is root.left is going to be again construct the binary search tree with the input that you have. Now we said just popping isn't going to be enough. We have to make sure the order of BST rules is maintained. That is, on the left side the value has to be smaller than the root, and on the right side the value has to be greater than the root. And to ensure we follow this, we have to now introduce lower and upper bounds when we are trying to construct. So the lower bound and the upper bound are going to be parameters that are going to be received, and initially when we make a call to this construct BST, which is then going to just return, is going to have the original list that has been received, and along with that the lower bound is going to be minus infinity and the upper bound is going to be positive infinity. So this is the initial trigger that we do, and after that what will happen is within this we will check for lower and upper bounds. And when we check for lower and upper bounds, we are going to say that if the lower value comparison fails, which will mean that the value is less than lower, or if the upper bound value comparison fails, which will say value is greater than upper, in that case I have to return null. I cannot proceed ahead because then it is not satisfying the valid use case, because this is the foundation that says BST has to have on the left subtree lower values, right subtree higher values. And if that is not happening, then you just exit. If it's happening, all good, you pick up the value. So what we can say is just let current node is going to be this popped value that you have, and you just build the root from that value. And you can then say that after you have popped, you have now the updated list with you. The first write will be calling with this traversal list, which will then pop the value within itself with the latest value. So then the write will consider this as the latest value which is supposed to be present. And we will make sure we are following the bounds. So what are the bounds? The bounds for the write subtree is that the value has to be greater than the root value itself. What is the root value that we have? The root value is value. So it has to be greater than the value of the root itself. And that becomes my lower bound. And the upper bound is whatever upper bound you have received. And similarly, for the left one, what is the upper bound? The upper bound is going to be that the value itself. So you just pass forward the lower bound, and the upper bound is the current node that you have received. And that's pretty much it in terms of the implementation that we want to follow here. We will just make sure that the data that has been received, if it is empty, we just return null to make sure that there is enough to work with. So if the traversal list dot length itself is not there, that is the length is 0, then we just return with a null. And that keeps a track of the upper bound that we want to keep here with us. And now that we have covered the whole flow, let's just recall the aim back here. The aim was that we want to follow our algorithm to serialize. The algorithm we followed was this post order traversal mechanism. With this post order traversal mechanism in mind, after we followed and created an array out of it, that array we converted into an encoded string with spaces. Now instead of spaces, you could have used another notations also. Only thing is that whatever notation exists here has to be used when we try to split the array back into its original form, because the data that will be received is going to be received as a string. And in terms of the time complexity that is going to be involved, it's going to have big O of n for doing this post order traversal here. So this is going to be time complexity of big O of n, because we will in worst case go through all the nodes that are available with us. For reconstructing the binary search tree again, that is also going to be big O of n, because in worst case we go through all the nodes again. And in terms of the space complexity for the traversal, it's also going to be big O of n, because we are going to utilize the call stack for the number of nodes that you have to make these recursive calls. And even for the construction again, it's going to be big O of n in terms of space complexity. So the overall space complexity and the time complexity for first serializing and deserializing is going to be big O of n plus big O of n, which is going to be big O of 2n, and which with 2 being the constant, you just get big O of n itself. And similarly, the time complexity also big O of n plus big O of n, which gives you big O of 2n, which then converts to big O of n. And that's pretty much it in terms of implementation. Thank you for watching. Please like and subscribe.